wanted to know if it was even,
Make the
you
X.
would do the test of symmetry for the y-axis, which is what?
Make the X negative.
Make the x's negative, right. Okay, Lucy? All right. Who else has a question about something? Finley?
Could you draw the logistic? Because on my test,
I
drew.
absolutely can draw the logistic function. The logistic function, the regular BFF. Now remember, we've talked about how we can move these things around, right? But just the standard logistic function has an asymptote at 0, an asymptote at 1, and it's a squiggly line in between like this. That is your basic logistic function.
Could you look at this?
I will after class. Is your asymptote on the axis? Or is it below the axis?
It's on it.
Okay, then it should be right. Yeah, if that's what you got, I'll look at it.
On homework 1.2, what is the right answer for 3B?
For 3B,
Yeah.
3B says, this is my function, and I need to know what the range is. I want the range, okay? So I want you just to think about this for a second. We could actually try to graph this. This is a little bit confusing because it's going to be flipped around because of the negative. Maybe it would be better to just think about it for a second. I have no idea what this is. There are some domain restrictions on it. But whatever I get when I do 4 minus x and take the square root, would you agree it's going to be 0 or bigger? Yes. So the minimum value for this guy right here is 0. Right? The smallest, this part can be a 0.
Yeah.
Yeah. So when I add 5 to it, the smallest the whole function could be is 5. So your range is everything from 5 to infinity, including 5. Now it's not 2 parts, they're not range. Range. For what?
1.2.
Uh-huh.
What was the answer for, how do you do 2D?
2D. 2D. This now is a domain question. Marin's was a range question. So we're looking at y's. Now we're looking at x's. So remember, where domain is concerned, we really have to watch out for denominators and radicals. So x minus 2 can't be 0, so x can't be 2. So on my number line, whatever is happening, I don't know, but it can't be 2. And then whatever's under the radical has to be positive. So whatever x is, it's got to be bigger than or equal to -5. So here's -5. I'm bigger than or equal to -5, but I have to skip over 2. So bracket -5 to 2. And then skip 2 and go from 2 to infinity.
How about C on 1.2?
2c?
Yeah.
X has to be bigger than or equal to 1. So it would be 1 to infinity with 1 bracketed. Right? That's just like, it's like part of this one. There's no denominator part to worry about. Okay? You like look at your paper and say, what was I thinking?
Yeah.
Yeah, I do that all the time. When I'm grading you guys' papers, I'm like, not you personally, but my students' papers, I'm like, where did that come from? All of a sudden there'll be a random 7 somewhere, and it's like, where did that come from? All right, what else? We'll do one more question. Who else has one? From some paper that I turned back, any paper that I turned back.
Can you do 4C on 1.4?
1.4?
The one
Okay, yeah.
due today.
Yeah, I'll go ahead and do it. I meant the stuff that already been due,
Yeah.
but what is it now I'm doing?
4C.
4C.
Because I work on these with Mr. Shaddy
Uh-huh.
and I've gotten a few of them wrong that I've done with him, so I don't even know how.
Okay.
Beyond him in.
Alright, so let's look at 4C. So some of you probably just turned this in, so if you wanna go get it, you can. If you haven't done it yet, do it along with us. And if you already got your paper back, fix whatever needs fixed. Okay, so what's the deal here? We have a sphere, and it's being inflated at a constant rate of 44 cubic millimeters per second. All right? So let's not complicate this. This part is easy. If we're putting in 44 cubic millimeters per second, what's the volume after 1 second? 44. After 2 seconds?
88.
88. So after t seconds, it would just be 44 t. I don't have a formula for that. That is literally the volume after t seconds, right? That's it. Now, when the volume is V, what is the radius R? Now, I do need a formula for this. When the volume is V, what is my formula for the volume of a sphere? 4/3 pi r cubed. Now, that equation is solved for R, or solved for V. Our job is to solve for R. So I guess I'll multiply by 3/4. Divide by pi. And take the cube root. So R is the cube root of 3V over 4 pi. That is the volume formula in terms of R. This is the volume formula in terms of V. But these are exactly the same, right? Just rearrangements. Okay. Write an equation that gives the radius as a function of time. Now, kids, this is a big calculus concept. This is the radius as a function of volume. So my variable here is volume. But what do I know about volume? Volume is 44T. So if I take that equation and I replace the V with 44T, now I know that cleans up, I'll clean it up in a minute, but now I have a volume equation that is in terms of time. And that's what it said. Give the volume, or give the radius in terms of time. Here it's in terms of V. I did my substitution, now it's in terms of time. So cleaning that up, that's going to be 4 to 44, 11, 33T over a pi. There it is. What is the radius after 5 seconds? I don't know, type it in on your calculator, but it's just 33 times 5 divided by pi, cube rooted. I said it was 3.74 minutes or seconds. It should be seconds, shouldn't it?
That's what I got.
Yeah, I don't know why I said that. Oh no, it's millimeters. It's millimeters. It's a radius. Yeah, so it's millimeters. Yeah. 3.74 millimeters. I'm solving for the radius. Okay? All right, so you put that one back, and now they'll all be right. Who got back your 1.4 paper and missed something in number 3 on that paper? Okay, so Sydney, would you tell me what you got? Which one, A or B?
B.
B, what did you get?
I got x squared and.
Wait, f of x equals?
Oh, I got for f of x, this is where I got it wrong. I got 3 and then in parentheses 3x plus 1.
That?
3x plus 1.
Okay. And then what did you put for G?
X squared.
Okay, so I want to talk about this, not because, I mean, I couldn't even remember who missed it. She's not the only one. There were other people who missed it. But I want to make sure you understand that taking a stab at it is great, but you need to check. So the question is, this is B. We want to do G of f of x. That's what the problem is. We want that to end up being 9x squared plus 3. So if she thinks this might be the answer, I'm gonna go ahead and make this 9x plus 3 to make my work a little easier. But if we think that's the answer, then Sydney, what we need to do is take your f and plug it into G. So in other words, we're gonna find G of 9x plus 3, which according to your function would be 9x plus 3 squared. Does that give me what I'm trying to end up with? No. So you know these are easily checked, right? Easy to check. I mean, no big deal. I'm not singling you out. I'm just saying, people, check it. It's easy to check. This didn't work. So what does that tell her? Go back and figure out something else here, right? So that you have the right combination. All right. Okay, let's put that stuff away. Let's get our notes back out and continue our conversation about inverses. Who remembers any point we made yesterday about inverses? We made a couple. Everybody remember?
Flipping the x and y.
They switched the x and the y. The reflection across the identity, which makes sense because that's the test of symmetry for the identity one. But the idea is very simple. If I am function f, and he is function g, and we are inverses, if I take the number 3 and change it into 7, so f of 3 is 7, then he's going to take the 7 and change it back into 3. That's what inverses do. So if you're ever confused, are these guys inverses? Take a number, plug it in, see what happens, plug that answer in, and see if you get your original number back again. Okay? That's what inverses do. Dom?
Oh, do we turn in our BFF goes back to you? Like, you don't
No,
go back.
you're gonna keep that one. Okay? You're gonna keep that one. Overall, those were quite good, folks. There's a couple of you that still need to spend some time memorizing that. They were pretty good. Okay, so I'm ready for E according to my records. So I'm going to try to graph this as carefully as I can. That's the point -2, 2. This is the point -1, -1. This is 0, 1, 2, 0, and 3, 1. All right, so would you say this crazy shape, this made-up random shape, is that guy a function? Yes, it is. That's a function. Is its inverse a function? No, why not, Sydney?
Because it doesn't pass the horizontal line test,
Exactly.
and its inverse would pass the
Exactly.
vertical.
Think about it, guys. If it doesn't pass the horizontal line test, then aren't there 2 points on that graph that have the same y? So when I do the inverse, those y's are going to become x's, and now it won't pass the vertical line test. So this is a function, its inverse is not. What is its inverse? Well, that's easy. What happens to this point right here? It becomes 2, -2. I'm just going to go in order. So this one, this one actually stays the same.
1, 1.
No, it stays exactly the same. Don't change any signs. Does it make sense that that point would stay the same? because isn't it on the identity line? Yeah. Okay, this one becomes 1, 0, 0, 2, and well, I'm not a very good artist, but can you sort of see what happened? It was kind of, I don't know, sitting kind of on the x-axis to start with, but now it's sitting on the y-axis. Sure, easy. Prove that f and g are inverses by showing that f of g of x is x and g of f of x is x. Okay. Alright, so f is x plus 3 over 4, and g is 4x minus 3. And we're going to prove that these are inverses. Okay, now a random kid out in the hallway might say, well, according to these functions, f of 5 would be 2, and g of 2 would be 5, so they're inverses. Is that a proof?
No.
No, because a proof has to prove that it's always true. It's true for 5. It could be true for 7 and negative 18 and the square root of 95 or something. It could be true for those things, but we're proving it in general. So we're going to build the composition f of g of x, and we're going to build the composition g of f of x. It is crazy to imagine, but sometimes things are inverses in only one direction. So we have to show both ways work. All right, so you remember how to do this? We start with g of x, which is 4x minus 3. And then we take that and plug it into f, right? Now don't panic, because this always works out beautifully if they're inverses. When I plug something into f, I put it right here. So 4x minus 3 plus 3 over 4. What does that end up equaling? The 3's cancel, right? And they end up with 4x over 4, which is x. Now I want you to keep in mind what you started with. In the beginning, didn't we start with an x? We changed it into something, and then we changed it back to an x. Done. Same thing here. Start with f of x. So f of x is x plus 3 over 4. Plug that into g. So 4x plus 3 over 4 minus 3. What has to happen? Has to equals x, has to equal x. Does it? Does it come out to equal x? Excuse me, it does. Yep. So, we're all set. You just did your proof, okay? All right, let's try B. Try it all by yourself. I'll try it too. Compare notes with your partner. You're gonna do exactly the same thing. Proving these two things are inverses of each other. So you're gonna build the composition both ways. By the way, what happens if I do this and I don't end up with x? They're not inverses, that's right. Or you need a
it's
6.
4, then you need
Yeah, so it's.
And see what you Does that smell good? Or candy canes?
Oh my. I did F of G first, and he ended up with this.
Yeah.
Anybody else get that? Okay. This is called a complex fraction. It's a big fraction that has little fractions in it. These are gonna happen to us a lot when we verify our trig identities. So I would suggest, you can do it any way you want, I couldn't care less how you do it. But the easiest way, the least writing, to take care of something like this, is to take each piece of the problem, and in this case there are 3 pieces, and multiply by the common denominator, which is x minus 1. Because what'll happen when you do that, can you see? You're gonna lose that, and lose that, and you know what I mean, we're little fractions, you still have the big one. So we have 1 plus x minus 1 over 1. See how easy that was? It didn't take up space, didn't have to write much. And what does that equal? X over 1. So it worked on that side, okay, Marin?
How did, the plus 1 come in on the top?
Need that one?
No, the 1 plus x minus 1. Where'd that first 1 come from?
That one is this one right here. It's all that's left when I multiply these together. Alright, I'm gonna do the next one now. So f of x is x plus 1 over x. G of that is 1 over x plus 1 over x minus 1. That is another complex fraction. Again, do whatever you want. I'm going to multiply by x. That cancels those. So I have an x on top, and x plus 1 minus x on the bottom. Which is exactly what we hoped. Life is good. Life is good. All right, one more problem in 1.5 to do. So 1.5 is going to be due on Friday. Try to wake up. All right, the formula for converting Celsius to Kelvin. You guys in chemistry probably know that, I do not. So X is the Celsius temperature. X is the Celsius temperature. And the formula for converting Fahrenheit to Celsius is so this is Fahrenheit. Find a formula for the inverse of C. Okay, find a formula for the inverse of C. So think of this as y equals 5/9 x minus 32. How will I find the inverse of that? Switch the x and y. and then solve for y. So maybe multiply by 9/5 and add 32. Does that look like a good inverse equation there?
Yeah.
Now, remember, the original equation took a Fahrenheit temperature and turned it into a Celsius. What does the inverse do? Take a Celsius temperature and turn it into Fahrenheit. I actually recognize those from some point in my life. All right, last question. Find K of C of X. So we're going back to our originals. There's K, there's C. We're finding K of C of X. Okay, so we'll start with C of X, which is that 5/9 thing. Now I'm gonna plug that into K. So won't I just have 5/9 X minus 32 plus 273.16?
Mm-hmm.
So 5/9 X minus, I'm just gonna add those together, so what is that, 160 divided by 9. So I got plus 255.38. Check my arithmetic, is that right?
Yeah.
Is that what you got? Okay, so what is that now? This is what I end up with when I plug my C function into my K function. Okay, so what did the C do? What did the C function do? C took a Fahrenheit and changed it into Celsius. So the ordered pairs for C were Fahrenheit, Celsius. Now what does K do, function K? Takes a Celsius temperature and turns it into
Kelvin.
So when I put those two together, what happens? I
Fahrenheit.
start with a Fahrenheit and change it into Kelvin. Yep, yep. That's a beautiful example of the meaning of the composition of functions. Beautiful, beautiful, beautiful. All right, 1.5, inverses and parametric. Kind of a two-pronged attack in there. We started out doing some parametric work and then we transitioned into inverses. All right? Deep breath, 1.6.
Oh, I was gonna ask to use the rest.
Important.
It really is. Okay, thank
Leave
you.
the telephone here,
Oh, I don't have that.
where you're gonna miss this rousing conversation
I'm sorry.
about transformations. When you were in geometry class, I'm sure you discussed this. There are three ways that we can transform graphs. One of them we've already talked about. We already talked about translations. We take them and we pick them up and put them down somewhere else. And how is that accomplished? In an equation, how do you move things? You add and subtract. When you add and subtract, you're moving it, okay? We can also reflect. Oh, I left one off the list. Talk about it, we'll go ahead and do these first. We can also reflect. Now, how do we reflect? What happens in the equation to reflect you? Well, if you want to reflect across the identity, you change x and y. If you want to reflect across an axis,
Multiply by negative.
we have a negative in there somewhere, right? Depending on where the negative is, determines whether you're flipped upside down or whether you're flipped this way. Okay? So a reflection doesn't pick you up and put you down. A reflection literally flips you over something. Whether it's the identity or an axis, you're flipped. And that's accomplished across the axes by negatives and across the identity line by switching the variables. A rotation is the most complicated. I'm not gonna deal much with them right now, but a rotation literally takes your picture and rotates it. So it doesn't pick it up, it doesn't flip it, it literally rotates it, like this. And that involves some trigonometry usually, because if you rotate something, it'll be like 330 degrees or something like that. So there is a matrix that will rotate things for you. We'll talk about that at a later time. The one I didn't include, and I definitely should have, is we can take a picture and stretch or shrink it. You know what I'm talking about?
Yeah.
So we could take our normal absolute value, let's say, that's your normal absolute value, and we could make it super skinny or super fat. Does anybody know what you do in an equation to accomplish a stretch or a shrink, right?
I didn't know greater than or less than 1.
You don't add it,
Or multiply it to
multiply
your
it,
x.
right, multiply it. So if we have a function and we add 2 to it, that's a translation. But if we multiply it by something, that would be a stretch or shrink depending on the size of the number I multiply it by. Perfect. All right, so consider y equals x squared, which is what? That's your parabola, that's your squaring function, that's a parabola. What happens in a
You translate it?
translation, where is it?
One zero.
What? I heard somebody say 1 0, I heard somebody say negative 1 0.
1 0.
Negative 1 0.
So this guy is over here at negative 1. Remember, whatever you do to x, whatever's happening with x, it's always the opposite of what you think. So I get it. When you see x plus 1, you think, oh, I'm gonna go over 1. Well, you're not. You're going back 1. Just like, I thought we looked at this one the other day. If we do something like this, if we multiply x by 2, remember the absolute value we looked at the other day? Do you remember that? We didn't? Was that I know I looked at it. Must have been with another class. Or not absolute, greatest integer. Didn't we graph a greatest integer the other day?
Yeah.
What did we notice about those steps?
They don't, yeah, they don't.
They were twice as long as they would normally have been?
Are you sure?
Maybe it wasn't.
I don't think so.
All right, get your calculators out, let's do it. I know I did it with somebody, geez. All right. So, here's what I want you to do. I want you to graph this. And then I want you to graph this. Now, you know where absolute value is? Greatest integer is in that same menu. So you go to math, number, and then I forget which option it is, but it's down there somewhere.
FN and.
Okay, and so put in 2x and hit graph. Yeah, put in 2x, hit graph, and then put in 1/2 x and hit graph. And then for your baseline, just do regular x. Keep a mental note of what's happening and tell me what's happening. Are you seeing steps?
Wait,
I don't know, we don't know where to find it.
FN int.
I said it's the same place as absolute value. So you go to math, numbers, go to math,
Oh, crap.
number,
I need to get out of
We'll pull something else
F int. Got it.
same place as absolute value.
Wait, now I'm out of my mind.
How do you get to that?
Great.
Now,
Oh, mode.
all of these, you should see steps. This is the normal one, And so you know, because you've memorized your BFFs, that these steps are 1 unit long, or 1 unit wide. Well, what happened when you did this one? They got shorter. These were squishy little steps. And then when you did this one, they got longer. So the point I'm trying to make to whoever was wrong about this problem we're doing is that when you do something to X, the result is always the opposite of what you would expect. If you see a 2X, don't you think it's gonna be twice as long? Sure, but it's not. It's half as long. Half X makes it twice as long. Whatever you do to X is the opposite of what you intuitively think. Okay? So, when I see X plus 1, I intuitively think, oh, plus 1, but it's always the opposite, so it's actually minus 1. Zoe's your hand up for some reason? No. Alright. Now, what about B? Back on the sheet now, put the calculator down. What are we doing on B? Let's put plus 1.
Make it up
Up
one
one.
line.
So it is the same parabola, but now it's vertex at 0, 1. By the way, you guys, when you are moving things around, please label the important points. So like I've labeled that and I've labeled that. Always label. So if it's a vertex or an asymptote, make sure you're labeling it.
This is 4.
What?
So on the first, on A, why is it that it's being translated across the x-axis, but on
No. It's being picked up 1 unit. There is no translation across an axis. There's a reflection across an axis. It's being picked up and moved 1 unit to the left. That's what's happening. A translation is cut it out, paste it somewhere else. There's no flip involved. Okay? All right. What's this one?
You reflected
This one is a reflection.
over the x-axis.
Because negatives mean reflections.
How would you
Right?
show?
And this means y is now the opposite sign than it was originally, so that's going to be going down instead of up.
How do you?
All right, let's try it with our logarithms. So stop and think what the original looks like. And then we're gonna figure out what the new one looks like. I like to draw my original. You don't have to do this. But I like to draw my original. This is my original picture. What happens here?
It's reflected over the y, or over the x.
Over the x-axis, it's turned upside down, right? So if I take this and turn it upside down, won't it look like this? The asymptote's the same, the intercept's the same, but now, instead of being an increasing function, it is going to be a decreasing function. It's turned upside down, going the opposite direction. All right, what about this one? This one next. Yeah. Moving.
To the right.
Pick it, cut it out, pick it up, move it 1 unit to the right, 1 unit to the right. So, go back to the original picture. That asymptote was originally at 0. Now that asymptote is at 1. The intercept was originally at 1, now it is at 2. The shape of the curve hasn't changed. It's exactly the same picture. Everything shifted over 1. We change the sign on X. Think back.
It's
When
not a
you change
reflection.
the sign on X,
Reflects
that's
on the Y.
symmetry about the y-axis. So this is a flip across the
Y.
y-axis. That negative is different than this negative. Can everybody see? So this is gonna take my original picture and literally fold it across the y-axis. Will that change the asymptote? No. What's it gonna do to that point right there? If I fold it across here, that's gonna become the point -1, 0. And you're folding it across, so isn't it gonna look like that? Just for fun, let's graph that one on our calculator. So go ahead, I don't know what kind of window you've got set up. But go ahead and type, find your ln key, everybody find it. So ln -x. Did you get something that looked like that?
Yeah.
Yep. Good job. All right, we're gonna do part 3, and then that's probably all we'll have time for today. Can I hear the size of a leaf? All right, here we go. Gonna do number 3. This is new stuff, or at least some of it's new. So I'm gonna take this random weird picture that I made up, completely made up, and I'm gonna go ahead and plot these points. Okay. So I've got a little down trapezoid, I got a standing upright trapezoid, and I have a little down triangle. And that is the function that I'm dealing with. Okay? Now, the first problem says, all right, there's my function. What happens when you graph its absolute value?
Everything has to be positive.
Everything has to be
Positive.
positive. Won't this be positive? So what we're saying is y has to be
Positive.
positive. So I am gonna look at each of these points and I'm gonna make the y's positive. Now, do I change the number? So if it's a -2 originally, it's still gonna stay at 2, but it's gonna be positive, right? Now, what if it's already positive?
It stays.
Okay, it stays the same. So would you agree that this trapezoid right here is not going to change?
Yes.
Yeah.
Aren't the y's already positive?
Yeah.
All right, what about this little triangle here though? It is going to go up, right? It has to become positive, so it's gonna look like this. In this trapezoid over here, would you agree the same thing? That it's gonna go up? I think of this function, it sounds kind of dumb, but I think of it as bottoms up. Because when you take the absolute value of a function, don't you bring the bottom up? Top stays up there. It's not a complete flip. Don't ever think that. It's not a reflection. It's just the bottom comes up because all of the y's have to become positive. Now, it's the other one that's a little bit wild and wacky. Now I'm taking not the absolute value of the whole function, but just the absolute value of the x's. Okay, now I want you to think about what happens. Let's just take a simple function, like y equals x plus 2. Now, if I said to you that I'm gonna take the absolute value of the x's, just the x's, what happens when I put in a positive 3? I get 5. What happens when I put in a negative 3?
5.
I still get 5. So in other words, if you're taking the absolute value of the x's, you are gonna get the same answers for every positive x as you're gonna get for every negative x. So, this side of the picture, from my hand over, will not change. Those are positive x's. And when you take the absolute value of a positive x, it doesn't change. So this part of the picture is going to stay the same. When you take the absolute, if x is positive, in other words, nothing happens. Whoops. If x is positive, absolutely nothing changes. Now, this always freaks us out. People say, oh, Miss Word is negative. Y is negative. The problem doesn't say anything about absolute value of y. It says x absolute value. So if these are the results that I get when I do positive x's, what is the result going to be when I do negative x's? Same thing. So you are going to have the exact same picture drawn on the other side of the axis. The answers, the y values you get for positive x's are going to be exactly the y values you get for negative x's. So if this is 1, 2, then negative 1 is going to give you 2. And if 2 gives you 0, then negative 2 is going to give you 0, because negative x's are going to give you the same value as the negative x's are going to give you the same value as the positive x's. Now, some of you are thinking, well, Mrs. Ford, what happened to like all this? Poof, gone, right? Because we no longer can put a negative x into our problem. We're only allowed to put positive x's into our problem now, because we're taking the absolute value. All right, we're backing out. Can't wait to get out of here. Look at you. You're hurting my self-esteem. Yes. No, no.
My dad,
Yeah, I don't know what. Why I thought that wasn't up there. Okay, I'll put that.
And then also, is there like an extra platform that's supposed to help you on CRVs? I have